Welcome back to the module Robot Dynamics. In the last class, we started off by deriving dynamic equation of motion using Lagrange-Euler equations. I gave you the example of 1 degree of freedom system including an oscillating spring mass system. Today we'll continue further with Lagrange-Euler formulation and do a 2 degree of freedom planar manipulator, just like a pendulum treatment the way we did it in last class, and do some interpretation of any dynamic equation of motion. So let us continue with today's class. Okay, so here is my system, which is exactly similar to a double pendulum. It's a point mass system again. So you see it has a bob which is hanging here. That is the first link, link 1, ending with a point mass which is here. And then you have a joint over here, you have a joint over here. So two links. So second joint is here, second link is here. That also ends with a bob which is here of mass m2. This one was of mass m1. So relative angle, you see with the frame, first link subtends an angle with the frame from the vertical, theta 1. Second joint angle is theta 2, that is the relative angle, you know. So exactly in a similar manner you can have a 2-link manipulator or an arm also. If it is a planar manipulator, it is exactly similar and similarly referenced also, but they are powered at the joint. In case of double pendulum, it is not powered. So we assume it is powered and we start our derivation using Lagrange-Euler formulation. And later on we may make torque equal to 0 and we can get dynamic equation of motion of a simple oscillating pendulum like this. Okay, this becomes a double pendulum in that case. So yes, let us begin. So we'll have to find out kinetic energy and potential energy in that case also. So kinetic energy of the links are, there are 2 links. So first link, it is exactly similar if you just exclude the second link from here. So what you see, it is exactly similar the way we did it in the last class. It was a simple pendulum. So for the second part of the link, that is the bottom link, okay, so it can be written as x2. X2 is nothing but displacement of point mass m2 along x-axis, so that becomes x2. So it is L1 sine theta 1. So it is acronyms. S1 is sine theta 1. I assume you remember that the way we did it in our forward and inverse kinematics classes. So exactly in a similar way. So it is L1 sine theta 1 plus L2 sine theta 1 plus theta 2. So this is your theta 1. So effectively this is your sine theta 1 plus theta 2. So it is that. So from here to here it is L1 S1. So total is this. Similarly, y2 can be written as cosine component, but it is directed downwards opposite to the positive y direction. So it is negative over here. So it is L1 C1 plus L2 C12. So downward it is negative. So x and y, that is the coordinates along x, coordinates along y. So taking derivative of that, I get the velocity directly. Velocity along x, velocity along y can be written like this. It is nothing but the derivative of this. Okay. Squaring and adding, I get resultant velocity of this, that is v2, that is x velocity square plus y velocity square. Square root of that should give me v2. So v2 is this. Okay, you can halt it here and you can just look at this, or you can derive it using your own pen and paper and use this to derive this, so that you can be very much conversant with these type of systems if you do all alone to any other system. Okay, so this is your velocity. So putting that over here in kinetic energy form, so it is kinetic energy of the second link, second mass system should be 1 by 2 m2 v2 square, 1 by 2 m2 v2 square. So that includes everything from here to here when we take v2 square. Okay, so combined together it can be written like this. So you have kinetic energy of first link and the mass. This is kinetic energy of second link and the mass. So total kinetic energy will be sum of those two, that is K1 plus K2. So that gives you this. Okay, so you got the kinetic energy. I have taken some common in the bracket also, so that it looks quite compact. Okay, so now taking the potential energy can be calculated as this and this. Let me just show you the figure once again. So this is how it was. So you see the projection along negative y should be, for the first link it is m1 g L1 cos theta 1, and for the second link it is sum of L1 and L2 projected towards negative of y axis, and that becomes your potential energy. So it is negative potential energy if the top one is the reference frame, that is origin is over here where x and y axes are intersecting. So you have negative potential energy with respect to that. So you get to this. Okay, so this is your potential energy, and kinetic energy is already there. So now you can quickly obtain your Lagrangian. Lagrangian is kinetic energy minus potential energy. So this minus this should give you this. Okay, so now that you have Lagrangian, you can quickly use Lagrange-Euler formulation to obtain the torque at each joint. This time it is 2 degrees of freedom. So when we want to obtain the first torque at the joint 1, you have to use theta 1 over here, and you get what is tau 1. Okay, you get tau 1. So in case of you want to obtain the torque at joint 2, it should be theta 2, which is here. Theta 2 should be used here, that is the joint angle which is there, and you get what? You get tau 2. You get what? You get exactly the torque at the joint 2. Okay, so that is how it is, and then I'll just use one of them one by one now. So starting with Lagrangian here. Okay, Lagrangian, and for the first joint variable using the Lagrange-Euler formulation, so that you know that was dou L by dou theta 1 dot. So it was against velocity. You can just see it here once again. Okay, so you should use this. So going one by one, so I have taken derivative of this, partial derivative of this with theta 1 dot, and I obtained this. Okay, you also can try doing it. Okay, and now the time derivative of this is to be done. So time derivative of this, again using this, I directly obtain this. Okay, so this is what I obtained. That is the first part of the Lagrange-Euler formulation. Now the second part. Second part is dou L by dou theta dot. Dou L by dou theta. So it is directly the joint angle variable. So it quickly everything becomes constant wherever you see theta dot. So wherever you have only theta, it is only this. Okay, so only this derivative is included here. So it gives me directly this one. The first part of the Lagrange-Euler and second part of the Lagrange-Euler formulation. So you have to take this minus this, that gives you tau 1. So tau 1 is using this, tau 1 is whole of this minus this, it gives you this. Okay, so this is your torque at joint 1, or this is the torque which is required to drive joint 1. Okay, in a similar way, I will start here once again for second link. Okay, and the second joint. So again you have to take derivative of this Lagrangian with respect to joint velocity, second joint velocity. So again wherever you see velocity, that is to be included. Only theta 2 is to be included, rest all becomes constant. Okay, so using that I quickly can obtain this. again time derivative of this gives me this. So this becomes the first part of the Lagrange-Euler formulation once again, and the second part is derivative of Lagrangian with respect to joint angle. It gives me this. So only the last part has got the variable theta, rest everything has got velocity, so those are treated as constant. So that comes here directly. Okay, so now using these two, this and this, I can complete my dynamic equation of motion, that is Lagrange-Euler formulation. So using this once again, this minus this, so it gives me tau 2 is equal to whole of this minus this. So finally I arrive to this. So this is your torque 2. So using both the torques, writing them together here, so this is tau 1, this is tau 2. So torque at joint 1, torque at joint 2, in order to obtain the velocities which are here, theta 1 dot, theta 1 double dot, and similarly for theta 2. So it should have this much of torque that is required to get to those velocities and accelerations. Okay, so this is torque 1 and torque 2. So this is just a scalar representation. Let me put it in a compact way. So if you can write it in matrix form. So tau 1 and tau 2 is clubbed here. Okay, and wherever you see theta 1 double dot and theta 2 double dot, those are the joint acceleration terms. So they can be written as this into 2 cross 2 matrix form, which is this. Okay, which is this. Okay, again you have joint and rate term, which is this one. This is theta 1 dot square, theta 2 dot square, that is pure single joint terms. So it can be again written as 2 cross 2 matrix, that is this one, and in the column you can write this. The third term is product of two angular velocities, that is theta 1 dot and theta 2 dot. So that can be again written as 2 cross 2 matrix into the product of angular velocities that goes here. And finally the last term doesn't have any acceleration or velocity term at the joint. It is just the torque which is due to the gravity component. You see only G are visible. Okay, so that is the four terms which are major terms of any joint torque. Okay, provided you don't have any external forces which are acting on the robot. So this is dynamic equation of motion for the robot. Okay, so this in general can be written as, not necessarily for a 2 degree of freedom robot, in general it is like this. So torque will go here, all the torques. Okay, you have an equivalent component which is similar to your moment of inertia term. This is known as generalized inertia matrix. Okay, GIM. Okay, and this is your acceleration term. So all the acceleration in vertical column, it can be written as matrix like this. So it is having all the inertia term, joint accelerations will go here. Next part you see it has theta 1 dot square, theta 1 dot square and theta 2 dot square. So it is mr omega square, similar to that. So it is known as a centripetal component. So this is the torque which is generated by the centrifugal forces which are created due to the motion of the links. So all the torques, they come here. So it is known as centripetal component. So that is this one. Okay, now the third part of this torque. So what is that? You see, it is product of angular velocities, theta 1 dot and theta 2 dot, or theta 2 dot and theta 1 dot. Both are equivalent. So I omega 1 into omega 2, you see you have I term, moment of inertia, similar to this. So you have exactly the way it is in any Coriolis torque component, if you have seen. So it is, this term is known as the Coriolis component. So it has product of angular velocities, and the last term is nothing but we have already derived it earlier using statics. In the module statics, we have already derived this, that is the torque which is due to the gravity. If you make whole of joint velocities and acceleration that is equal to 0, that means if the robot is at rest, so this is the torque which is going to come at the joint. So this is exactly the same what we have derived earlier, okay, in module statics, that is a torque compensation or compensation, gravity compensation we call it. So it is exactly that. So these are the four major terms which form any dynamic equation of motion for any robot. So only thing is the size of these matrices will change. So this should be n by n, that is number of degrees of freedom cross number of degrees of freedom, that is here. Okay, similar should be this and this. The last one is n cross 1 and torque is also n cross 1. Got it? So this is general equation of motion, and let us just interpret how does it look like if it is put to a physical system. Okay, so in compact notation it can also be written as, so tau is equal to I, this is generalized inertia matrix, theta double dot h theta 1 dot square theta 2 dot square, it is function of those two. So that is centripetal component, and this one is Coriolis component, so that is theta 1 dot into theta 2 dot. So it is that term which is there. So it has all the terms which has this, okay, and final one is nothing but it is just a function of joint angles. So all of them are dynamic in nature, they keep changing with the pose, different velocities it changes. Okay, so even if it is static at different angles you see different torques. So that is dynamic in nature. So now let us put all these to physical robots. So this is the first term. So this is your equivalent component to moment of inertia. So that comes here. Okay, so you see at each and every state of the robot for a given joint angle, so it has its own structure. Okay, so if it is fixed, if you freeze this joint angles, so robot looks like this or robot looks like this. Okay, at different angles it will have different shape. So if at all you want to analyze what is the torque over here, so it treats whole of the body frozen. Okay, so the inertia component will have a value over here that treats, that basically has the moment of inertia which is treating rest of the robot frozen. Okay, so that term will come here. So this term will assume whole of the robot is frozen, and that gets multiplied by the term theta 1 double dot. Okay, I theta double dot. So this is theta 1 double dot, this is the moment of inertia considering whole of the robot frozen, only the joint 1 is moving, so that term comes here. Similarly, the last term which is here will assume there is no other link after that, so that is the only joint that exists, the joint, last joint which is there, so that gets multiplied with the last joint acceleration. So this is the moment of inertia of the last link only. Okay, so all the intermediate terms, the diagonal terms, are moment of inertia, primary moment of inertia, principal moment of inertia about the link itself. Okay, and considering the links which are after this as frozen. Okay, so that comes here, and all the moment of inertia should be represented in a single frame. We prefer putting them to the first frame which is attached to the ground. So using the kinetic energy, using the potential energy, everything should be calculated with respect to the frame which is attached to the ground. So you already know how moment of inertia can be transferred to any frame. So it is QI Q transpose. So it is exactly in a similar way you can calculate it to convert. If it is in the moment of inertia normally is expressed in its own frame, so it can be transferred to the fixed frame using the transformation matrix Q. That is nothing but you can extract it from the forward kinematic transformation, so that helps you to transfer it to the fixed frame, okay, that is attached to the ground. Okay, so that is how you can do. And also potential energy, you have to use vector matrix form to convert it all to the fixed frame. So and then you can do all this. So kinetic energy, potential energy, everything can be converted to the root frame, and then you have to calculate them and take Lagrangian differential of that and find out the torques. So this is how it is done. So this is the physical meaning of any generalized inertia matrix. Okay, so that is what it means. And then the second one, the second term, that is the centripetal component. So that again assumes if it is for any particular angle. So you see, if it is for this angle, so it assumes the whole of the structure is fixed in this case. So this is the mass, so that becomes the centripetal force which is acting, trying to pull it here. Centrifugal force is extended like this, and then that creates the torque which is over here. So this is the centrifugal force, and this is the arm which is there. So R1C2 into F cent should give me the torque that comes here due to this centripetal force. Similarly, so that if it is not passing through the origin, that will also create torque at joint 1. So these are the forces that will create torque at any joint if it is moving. Okay. Similarly, the last component, that is the Coriolis component, how does it arise? So first link is okay, but the second link, you see what kind of motion is this? It has a revolute motion or rotating motion, as well as because of motion of joint 1, it has a linear velocity also at any instant of time, because this is the distance, this moves with theta 1 dot, so it has a value which is like this, and it has a rotating thing also. So this has a complex motion of linear and rotating motion. So this is on the rotating reference frame. So you have a Coriolis component that comes here. Okay, and the last thing you have analyzed already in very much detail in our earlier module. What was that? That is statics. You saw how gravity compensation torque can be generated. So if there is no velocity and acceleration, all these terms will become equal to 0, and the torque that will remain is only due to the gravity component. Okay, so that is the physical meaning of all the terms which are here. Okay, so there are some limitations. Even though we have arrived at dynamic equation of motion that gives you a torque for any kind of motion which a robot makes. Okay, but in case of industrial robot, it has a high gear reduction ratio. So if at all you have first link, and then you have a joint which is having high gear ratio, and then you have a second link which comes here. So a small amount of torque is quite good enough to drive this link, because you have a high gear ratio ranging from 300 to 100. Okay, so that is the normal gear ratio which is there at each joint, normally in case of any industrial robot. So you get a very poor torque reflectance. So whatever is torque which is generated due to this is reflected very badly over here. So you see very small amount of torque that comes here. So that physically isolates all the joints, okay, all the links from the previous link. So it can be treated independently. Okay, so it is this type of robots are not back drivable most of the time. You cannot apply forces over here and try to rotate it, because it is very high gear reduction ratio, and they have friction also inbuilt to that because of the friction between the metal elements which are in surface to surface contact. Even after a huge amount of lubrication which are there, they have friction, and they don't allow any back drivable thing. Due to its own weight, it will poorly fall very slowly. Ultimately it will touch the ground. But so that is the reason it normally isolates the second link from the first link to the zeroth link like that. So they can be treated like a single input and single output controllers. So they are dynamically decoupled system. Okay, decoupled system. So that is what is advantages and allows us to run this type of robots directly in position and velocity control mode. You just give the joint velocity and position command, and the robot goes to the commanded position. You can calculate the joint velocity and positions using inverse kinematics and Jacobians. So you can directly feed in those rates over here, and you see the end effector rates and the positions varying. So it won't depend too much on dynamics in that case. So as compared to the dynamic torque that actually comes onto the motor is very less. Okay, so you only need to drive the joints in this. So most of the industrial robots supports commanding for position and velocity only. You cannot command it to use a particular joint torque and drive the end effector or even the link. Okay, so having a torque using dynamic equation of motion doesn't help much when you are using a ready-made kind of industrial robots in your lab. Okay, or in the industry also. So this makes the torque computation using LE or Newton-Euler formulation not much applicable for its control. Okay, however, the joint position controllers still use precise joint model, robot electromechanical model internally to control its joints. Okay, that doesn't mean a whole of the exercise that we did is meaningless. So in order to achieve very high amount of accuracy and positional repeatability, this kind of controllers are still there at the joints. Okay, at the joint level. Okay, but yes, the manufacturers normally they don't give you access to run the robots using torque command way. Okay, so you can only command for position. So obtaining precise robot models using CAD or using any identification experiments are not very precise. So even because robot joints links are very complex, so you hardly know the exact moment of inertia and the mass center location or even the mass at times. Once it is assembled, it is very difficult to find out even the mass. Okay, because you have huge amount of electronics that is there inside the links. You have gearboxes, you have belts, you have other transmission system, concentric shaft and many other things. So that makes it very complex. So it is not a uniform density so that you can get through the CAD. Okay. The center of mass location, mass, moment of inertia details are not shared with the end user. That is only for the manufacturer's purpose, and for maintenance sometimes they do use, but they don't allow end user to drive the robot using these parameters. Okay, so what we have in hand is only position and velocity control that we can do. Okay, again, due to the complex transmission, as I have said, electronics, cables within the link further make it difficult to obtain these details. Okay, so using torque control to drive any robot is also highly unsafe. It is unsafe because it is very sensitive. That type of running will make your robot very sensitive to any external parameters. Like even if you put a small supplementary load on one of the link, the dynamics changes and your control things will change. So whatever torque you are feeding, that will not be good enough to obtain particular joint velocity or acceleration or any joint position. Okay, so that directly affects the end effector parameters also, like end effector position, velocity and acceleration. So your system is highly unmodeled and it is highly uncertain in this case. So that is the reason, due to safety and other factors, in industrial robots it is not allowed by the manufacturer. So yes, if at all you are making a cobot or collaborative robot, this becomes very useful, this kind of knowledge. And if you make your own robot, you want to make one of your own, this knowledge will be very useful. And even if you want to understand the behavior of your robot, why putting a supplementary load beyond certain value which is prescribed by the manufacturer goes beyond that value, why your robot should not behave well, why load should be within the prescribed limits, why wire should be lashed properly. Okay, so there are many reasons, many answers that you will get out of this knowledge. Okay, so that's all for today's class. In the next class, we'll start with another approach for obtaining equation of motion. So that is Newton-Euler approach that we'll be doing. For PhD students and for research students, for UG students who want to go for research, they should quickly follow any book like Professor Saha's book, like Introduction to Robots should be good enough, or any book you feel like, so you can follow that book. And definitely I would suggest go for vector matrix approach for obtaining equation of motion using Lagrange-Euler formulation. Why? Because the way we did it, we directly took derivative. It is good for symbolic understanding of your system, and expressing at least for 2 degrees of freedom it was trivial. But if the system goes in 3 dimension and you have to program it for dynamically obtaining the torques, so it becomes very difficult. So this method is not suitable for programming for equation of motion, to obtain equation of motion and dynamic torque. So I would suggest go for vector matrix approach to obtain the torque, to obtain equation of motion. So that will also support programming your robot for this kind of approaches to control your robot. Okay, so that is an additional reading I suppose you should go for. Okay, so that's all for today. Thanks a lot.